The severe damage observed in this incident was primarily due to incorrect wiring by the power company. The neutral conductor from the power company's transformer was inadvertently connected to an isolated bus with no other connections, while the customer's neutrals were connected to a separate ground bus that only had two number 1/0 conductors. When the electrician shorted the panel, the current had nowhere to flow through the neutral back to the transformer. Instead, the entire fault current of 1200 amps was forced to flow through the equipment and the burnt conductors. The extended length of the neutral conductor and its isolated nature increased the impedance of the path, causing a significant voltage drop and intense heat buildup. Since no fault current was flowing through the neutral, the power company's transformer perceived the fault as an additional load. This resulted in the transformer delivering more power to the site, further exacerbating the situation. Here's the chain of events. Firstly, the electrician shorted the panel, creating a high impedance fault path. Secondly, the 1200 amps of fault current flowed through the equipment and burnt conductors, melting the panel. Thirdly, the extended neutral conductor and increased impedance led to excessive heat buildup. Fourthly, the power company's transformer, receiving no fault current, interpreted the fault as a load and increased power delivery. Finally, the additional power intensified the heat and caused further damage, including burning the service wires in the vault. The power company corrected the wiring by connecting the neutral conductor from the transformer to the neutral bus bar. This provided a proper path for fault current to flow back to the transformer, preventing similar incidents in the future. In a properly wired system, the neutral conductor provides a low impedance path for fault current to return to the source, which is the transformer. This low impedance path is essential for the rapid operation of overcurrent protection devices such as circuit breakers or fuses. These devices are designed to interrupt the flow of current when it exceeds a certain threshold, preventing damage to equipment and minimizing the risk of electrical shock. When a fault occurs, such as a short circuit between a phase conductor and ground, a large amount of current will flow through the fault path. In a properly grounded system, this fault current will return to the source through the neutral conductor. The low impedance of the neutral conductor ensures that the voltage drop along the path is minimized, allowing the fault current to rise rapidly. This rapid rise in fault current will quickly trip the overcurrent protection device, isolating the fault and preventing further damage. In the case described, the neutral conductor was not properly connected, which created a high impedance fault path. This high impedance path limited the flow of fault current, preventing the overcurrent protection devices from operating as intended. As a result, the fault current continued to flow through the equipment, causing excessive heat and damage. The importance of proper grounding and bonding in electrical systems cannot be overstated. Grounding provides a low impedance path for fault current to return to the source, while bonding ensures that all metal parts of the electrical system are at the same potential. Together, grounding and bonding minimize the risk of electrical shock and prevent damage to equipment. The National Electrical Code, or NIC, provides detailed requirements for grounding and bonding electrical systems. These requirements are based on years of experience and research, and they are designed to ensure the safety and reliability of electrical systems. Some key aspects of grounding and bonding include the size and type of grounding conductors, the methods for connecting grounding conductors to equipment and structures, and the requirements for grounding electrodes. Grounding electrodes are devices that are used to connect the grounding system to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the minimum size and type of grounding electrode that must be used, depending on the size and type of electrical system. In addition to grounding, bonding is also essential for electrical safety. Bonding involves connecting all metal parts of the electrical system together, including equipment enclosures, conduit, and metal structures. This ensures that all metal parts are at the same potential, which minimizes the risk of electrical shock. The NEC provides detailed requirements for bonding electrical systems, including the size and type of bonding conductors, the methods for connecting bonding conductors to equipment and structures, and the requirements for bonding overcurrent protection devices. In addition to the NEC, there are other standards and guidelines that provide information on grounding and bonding electrical systems. These include standards from the Institute of Electrical and Electronics Engineers, or IEE, and publications from the National Fire Protection Association, or NFPA. These standards and guidelines provide more detailed information on specific aspects of grounding and bonding, and they can be helpful in designing and installing electrical systems. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the requirements of the NEC and other applicable standards and guidelines, it is possible to minimize the risk of electrical shock and prevent damage to equipment. In the scenario described, the improper connection of the neutral conductor created a dangerous situation that could have resulted in serious injury or death. The fact that the electrician was burnt highlights the importance of proper grounding and bonding in electrical systems. The power company should have inspected the wiring before energizing the system to ensure that it was properly grounded and bonded. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factors. Electricians and other electrical workers should be properly trained in the principles of grounding and bonding, and they should be aware of the potential hazards associated with working on electrical systems. They should also be provided with the necessary personal protective equipment, or PPE, such as insulated gloves and safety glasses, to protect themselves from electrical shock and other hazards. Regular inspections and maintenance of electrical systems are also important for ensuring their safety and reliability. These inspections should include a visual examination of the grounding and bonding system to ensure that it is in good condition and that all connections are tight. Any damaged or corroded component should be replaced immediately. In addition to visual inspections, electrical testing should also be performed on a regular basis. This testing can help to identify potential problems with the grounding and bonding system before they become serious. Some common types of electrical testing include ground resistance testing, continuity testing, and insulation resistance testing. The results of these tests can be used to identify areas where the grounding and bonding system needs to be improved. The incident described highlights the importance of proper grounding and bonding in electrical systems. By following the requirements of the NEC and other applicable standards and guidelines, it is possible to minimize the risk of electrical shock and prevent damage to equipment. Regular inspections and maintenance of electrical systems are also important for ensuring their safety and reliability. In conclusion, the power company's error in connecting the neutral conductor led to a dangerous situation with severe consequences. This incident underscores the critical importance of adhering to electrical codes, performing thorough inspections, and ensuring proper grounding and bonding in all electrical installations. The correct wiring configuration would have provided a low impedance path for fault current, allowing overcurrent protection devices to operate effectively and prevent extensive damage. The misinterpretation of the fault as a load by the transformer further amplified the problem, leading to the complete meltdown of the panel and damage to the service wires. This situation emphasizes the need for qualified personnel to perform electrical work and for rigorous quality control measures to be in place to prevent such errors from occurring. The incident also serves as a reminder of the potential dangers associated with working on energized electrical equipment and the importance of using appropriate personal protective equipment. The proper functioning of the neutral conductor is paramount for electrical safety and system integrity. The neutral provides a return path for current in a three-phase system, and it also serves as the reference point for voltage measurements. In a properly balanced three-phase system, the current in the neutral conductor should be minimal. However, if the system is unbalanced, or if there are nonlinear loads present, the current in the neutral conductor can be significant. The size of the neutral conductor must be adequate to carry the expected neutral current without overheating. The NEC provides specific requirements for sizing neutral conductors, depending on the type of load and the characteristics of the electrical system. In addition to carrying current, the neutral conductor also plays an important role in grounding. In a properly grounded system, the neutral conductor is connected to ground at the service entrance. This connection provides a low impedance path for fault current to return to the source, which is essential for the rapid operation of overcurrent protection devices. The NEC specifies the requirements for grounding the neutral conductor, including the size and type of grounding electrode that must be used. The grounding electrode is a device that is used to connect the grounding system to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC also requires that the neutral conductor be bonded to all metal parts of the electrical system, including equipment, enclosures, conduit, and metal structures. This bonding ensures that all metal parts are at the same potential, which minimizes the risk of electrical shock. The NEC provides specific requirements for bonding the neutral conductor, including the size and type of bonding conductors that must be used. The proper functioning of the neutral conductor is essential for the safe and reliable operation of electrical systems. By following the requirements of the NEC and other applicable standards and guidelines, it is possible to minimize the risk of electrical shock and prevent damage to equipment. The power company's error in connecting the neutral conductor in the incident described led to a dangerous situation with severe consequences. This incident underscores the critical importance of adhering to electrical codes, performing thorough inspections, and ensuring proper grounding and bonding in all electrical installations. The electrician's injuries serve as a stark reminder of the potential hazards associated with working on energized electrical equipment and the importance of using appropriate personal protective equipment. The lessons learned from this incident should be shared with all electrical workers to prevent similar incidents from occurring in the future. Electrical safety is everyone's responsibility, and it is essential to take all necessary precautions to protect ourselves and others from electrical hazards. The proper installation and maintenance of electrical systems are critical for ensuring the safety and reliability of our electrical infrastructure. By working together, we can create a safer environment for everyone. Let's examine several possible causes of electrical problems and how to test for them. Firstly, there can be faulty wiring. Inspect wiring for damage, loose connections, and proper insulation. Use a multimeter to check for continuity and voltage levels. Secondly, there can be overloaded circuits. Determine the load on each circuit and ensure it does not exceed the breaker's rating. Use an ammeter to measure current draw. Thirdly, there can be ground faults. Use a ground fault circuit interrupter, or GFCI, tester to check for ground faults and outlets. Inspect grounding connections for corrosion and proper bonding. Fourthly, there can be voltage fluctuations. Monitor voltage levels with a multimeter or power quality analyzer. Investigate the source of voltage fluctuations, such as loose connections or equipment malfunctions. Fifthly, there can be damaged components. Inspect electrical components for signs of damage, such as discoloration, cracks, or burn marks. Use a multimeter to test the functionality of components, such as resistors, capacitors, and diodes. Sixthly, there can be improper grounding. Verify that grounding conductors are properly connected and sized according to code requirements. Use a ground resistance tester to measure the resistance of the grounding system. Seventhly, there can be loose connections. Tighten all electrical connections to ensure proper contact. Use a torque wrench to tighten connections to the manufacturer's specifications. Eighthly, there can be water damage. Inspect electrical equipment and wiring for signs of water damage. Replace any damaged components and dry out the affected area. Ninthly, there can be pest infestations. Inspect electrical equipment and wiring for signs of pest infestations, such as chewed wires or droppings. Eliminate pests and repair any damage they have caused. Tenthly, there can be code violations. Ensure that all electrical installations comply with local and national electrical codes. Consult with a qualified electrician to correct any code violations. Testing electrical systems requires a systematic approach to identify and resolve problems. By following these steps, you can ensure the safe and reliable operation of electrical equipment. Understanding the root causes of electrical issues is crucial for effective troubleshooting and prevention. Proper maintenance and regular inspections are key to maintaining a safe electrical environment. In addition to the troubleshooting steps mentioned above, it is important to consider the specific type of electrical system being tested. For example, the testing procedures for a residential electrical system will be different from those for a commercial or industrial electrical system. Residential electrical systems typically operate at 120 volts and 240 volts, while commercial and industrial electrical systems may operate at higher voltages such as 480 volts or even higher. The higher voltages used in commercial and industrial electrical systems require specialized testing equipment and procedures. It is also important to consider the type of equipment being tested. For example, the testing procedures for a motor will be different from those for a lighting fixture. Motors typically require testing for insulation resistance, winding resistance, and motor rotation. Lighting fixtures typically require testing for voltage, current, and ballast operation. In addition to the specific type of electrical system and equipment being tested, it is also important to consider the environmental conditions. For example, testing electrical equipment in a damp or humid environment may require special precautions to prevent electrical shock. It is also important to consider the ambient temperature when testing electrical equipment. Extreme temperatures can affect the performance of electrical components and may require adjustments to the testing procedures. Finally, it is important to document the results of all electrical testing. This documentation can be used to track the performance of electrical equipment over time and to identify potential problems before they become serious. The documentation should include the date of the test, the type of equipment tested, the testing procedures used, the results of the test, and any corrective actions taken. Proper documentation is essential for maintaining a safe and reliable electrical system. By following these guidelines, you can ensure that electrical testing is performed safely and effectively. Remember to always consult with a qualified electrician if you have any questions or concerns about electrical safety. The safety of yourself and others depends on it.